Hello everybody and welcome. This is the first video in a three-part video series walking you through making your own demo boards for the 18F4550 and programming the 18F4550. This video series is ideal for you if you've worked with other microcontrollers before, maybe Atmel, Renesas, etc., or something similar like an Arduino board, and you'd like to learn to work with microchip PICs. Or if you've worked with electronics before otherwise and would like to begin using microcontrollers, or if you've written desktop software and you'd like to start writing embedded software and working with circuits, or even if you haven't worked with electronics at all before, but you'd like to jump into the deep end and learn to work with microcontrollers first, which is a great place to start. In this last case especially, you might have to refer to some of the other sources I'll mention throughout the video. So for the first video, what we're going to do is we're going to get a LED blinking with the simplest possible circuit that we can use for the 18F4550. In the second video, we're going to add to that circuit both analog and digital input, and then in the third video, we're going to demonstrate the USB capabilities of the 18F4550. Throughout any of these videos, please check my website, www.18f4550.com. I'm going to have diagrams, pictures, parts lists, etc. all up there for you. You can download them, print them out. Hopefully that'll be helpful. Also, my YouTube channel is 18F4550 videos. So, what is the 18F4550? The 18F4550 is a great microcontroller made by Microchip. You can see their website, www.microchip.com. The full name is the PIC18F4550. Usually I omit the PIC part and just say 18F4550. A microcontroller, for those who don't know, is you could roughly think of a microcontroller as something equivalent in processing power and memory to a desktop computer of a generation ago, perhaps 25 to 30 years ago, but it's on a single chip. So for example, this here is a picture of the 40-pin through-hole version of the 18F4550 that we'll be working with. So why is the 18F4550 so great? Well, there's lots of reasons. It has 40 pins, at least the version that we'll be working with does. 32K of flash program memory, 2048 bytes of SRAM data memory. The clock can go up to 48 megahertz with an external oscillator, which is blazingly fast for a microcontroller. And it also has internal circuitry to assist you with all the following, although you still have to write the firmware. Analog to digital conversion, pulseless modulation, voltage comparison, interrupts, and timers, and the big kahuna, USB. In fact, if you do an internet search on 18F4550, the very first thing that comes up after 18F4550 itself is 18F4550 USB. So if you're doing a project, you want to add USB to it, 18F4550 is probably your best bet. Also, it does USR communication, I2C, SPI. I could go on, but rather than do that, let's dive in and get started. So let's get a LED blinking. To do that, here's the steps involved. We're going to need to start with our parts list, and then we're going to have a circuit diagram, then we're going to breadboard our circuit, and then we're going to write a program to load into the 18F4550. Then we're going to load that program into the 184550 and test it, and then to have something more permanent, we're going to perfboard our circuit. So let's get to that. So here we have our Blink Demo Boards parts list. If you like, you could go to www.18f4550.com for a printable version of this parts list. So for each part, I've listed the name, description, suggested supplier, and matching supplier's part number. And for most of these parts, you could go with an equivalent from a supplier of your choice or use what you already have on hand if you prefer. But for these first two parts especially, the 18F4550 and the PIC-Kit2 or the PIC-Kit3, I would definitely recommend getting those from Microchip Direct. That's Microchip's direct sell site for their products. The address is www.microchipdirect.com. Let's take a quick look at that. So if we go to www.microchipdirect.com, and here's our opening window here, so we type in 18F4550, and the second choice here, PIC18F4550, that's what we're looking for. And the next page is going to bring up multiple versions of the 18F4550, which varies on things such as package type. So let's take a look at that. Package type PDIP, that means plastic dual inline package, in other words the through-hole version. And 40 is the pin count, so that's a 40-pin through-hole part. Some of the other packages that are available are QFN and TQFP. Those are surface mount chips, which we're not going to get into at the moment. So we'll filter on package type PDIP, and that will get us down, I believe, to two different chips. And there we are, a PIC18F4550 IP and PIC18LF4550 IP. Now the L is short for low power, so this particular version of the 18F4550 you could use with less than 5 volts, but we'd probably best not get into that. Let's stick with the good old traditional through-hole part 40-pin 5-volt version of the 18F4550, and that's this one here. Then we got to choose our quantity. I'd recommend you get at least 3, 4, 5 would be better. You're definitely going to want to have some extra chips on hand because you're going to have multiple projects going and so on. So once we have our chips, the next thing we have to do is decide to get the PIC18F4550 or the PIC18F4550. So let's take a quick look at the comparison of the two. The PIC18F4550 and the PIC18F4550 are the programmers for microchip PICs. The PIC18F4550 is more user-friendly, whereas the PIC18F4550 is more sensitive to not harming lower voltage chips, and I'll explain the difference. The PIC18F4550, when you connect it to a circuit that has a microchip PIC in it, it attempts to auto-detect it, and to do that auto-detection process, the PIC18F4550 has to apply a voltage to the board. In doing so, if you connect the PIC18F4550 to a circuit that has a low voltage chip, the auto-detect voltage the PIC18F4550 applies might harm the chip. The PIC18F4550, which is newer and intended to work with the newer 3.3 volt chips, is much more friendly to not harming 3.3 volt chips. But as goes along with that, the auto-detect process is not as complete, so it's really not as user-friendly to use the PIC18F4550. Some other differences are the PIC18F4550 is $35, whereas the PIC18F4550 is $45. The PIC18F4550 is older, so it's more refined, but it might not be supported as long into the future, whereas the PIC18F4550 is newer and is going to be supported longer. Also, the PIC18F4550 programs most PICs, including the PIC18F4550, whereas the PIC18F4550 microchip states will program all PICs. So if we go to www.microchipdirect.com, we should be able to find the PIC18F2 and PIC18F3 pretty easily. When we type in PIC18F2, there we go, PIC18F2 microcontroller programmer. I'll open that in a separate window. And then also the PIC18F3. Also, when you do a search on these PIC18F2 and PIC18F3, you'll see these packages that Microchip offers where they'll include a demo board with it for a relatively small additional cost. The Microchip demo boards are great. I have a few of them, but really you're going to learn the most about working with the PIC18F4550 and constructing circuits for it if you make your own demo board. Personally, that's what I would suggest. But if you want an option where you don't have to do any soldering at all and you can start writing software immediately, these kits are something to consider. So here's our PIC18F3, $45, and then the PIC18F2 is $35. So you could choose either based on your preference. Also, it'd be a good idea to watch through the rest of this video series, and then you can see the process of programming the PIC18F4550 with the PIC18F2 and 3, and decide which one you prefer at that time. So referring back to our parts list, once we've gotten the rest of our parts also from either my suggested supplier or a supplier of your preference, then we're ready to consider our circuit diagram. So here's our circuit diagram for our Blink demo board. But before we consider our diagram, let's first get the PIC18F4550 datasheet. So if we go to an internet search, PIC18F4550 datasheet, and let's choose the first option. That'll take us to the microchip page with the PIC18F4550. Here you notice it lists specs and so on. We're going to look for the section data sheets. Right click on that and save target as, and save the data sheet for the PIC18F4550 to somewhere very convenient such as your desktop, because you're going to refer to it often. I already cheated and downloaded it ahead of time. And it's going to take a moment to open because it's a big document, over 400 pages. So you're not going to want to print the whole thing out at 438 pages. However, you're definitely going to want to print some parts of it out. Now you'll notice there's a nice table of contents here. One of the really strong parts about using microchip products is that the documentation for their chips is excellent. It gets into all types of different the features the chip has and provides nice diagrams and explanations and everything. One page you definitely will want to print out pretty much immediately is page 4, because that's the pinout for it. So here's the particular chip and package that we're using, 40-pin PDIP package. Try not to get confused with some of the other chips that are mentioned in the same datasheet. It's the same datasheet for the 2455, 2550, 4455, and 4550. Of course, we're really only concerned with the last of these. The other chips have either less memory or fewer pins. At the bottom of page 3, there's a comparison of the 4 different chips mentioned in this document. But anyhow, what you want to do is print out page 4 and focus on this part here because that's what we're going to be using. So starting with this pinout, which I basically just reproduced here, and then the rest of the circuit. So for each of these pins, they're labeled all these different fancy looking things. Try not to get too intimidated by that if you haven't worked with microcontrollers before. For example, pin 33 is RB0, AN12, INT0, FLT0, SDI, and SDA, depending on how you have the chip configured. We'll get to how to configure it in software later on. But anyhow, the idea is that there's so many functions that this chip could do. If each one of these was on a separate pin, the chip would be hundreds of pins and it would be unmanageable. So Microchip has combined the functionality of all these various different things that can be done with multiple functions on one pin. So without getting into all these in detail, what we want to look at overall is for basic input-output, we want to look at our ports. And those are ports RA, RB, RC, RD, and RE. Now each port has multiple pins. For example, port B has pins RB0, 1, 2, 3, 4, 5, 6, and 7. So in our case, we're going to have 4 LEDs that we're going to blink, and to make it easy on ourselves to keep track of it, we'll simply connect LEDs 0, 1, 2, and 3 to RB 0, 1, 2, and 3, which are pins 33, 34, 35, and 36 on the chip. Of course, we need a resistor in series with those LEDs to limit our current. Also, we need to provide power. There's a power pin on both sides of the 18F4550, pin 32 and pin 11. Those both go to plus 5 volts. Now, when I have plus 5 volts on this diagram, that doesn't mean a separate power supply, which I mentioned in the notes up here. There's only 3 things that go to power. Also the programming connector, I'll get to that in a minute. But the plus 5 volts means connect that to your power bus, and then when we're actually testing the circuit, the programmer will provide power to the circuit for us. So no external power supply is needed. So continuing on here, there's 2 grounds on the 18F4550, pin 31 and pin 12, and then we also want to add a smoothing cap from pin 11 to ground, or alternatively you could place that on pin 32 to ground to provide a stable voltage for the chip. So other than the parts already mentioned, LEDs, smoothing cap, powers, and grounds, the only remaining part here is this programming connector. So the pins on the PIC 2 or 3, it's going to be a 6-pin device. So that's why I've illustrated the 6 pins here. The first pin is the programming voltage, and I'll use white in my diagrams for that. You could choose whichever colors you like though, but I prefer white, red, black, green, and yellow for these 5 pins. The 6th pin is an auxiliary pin that's really only there for historical reasons. We won't be using that pin. You can just leave that unconnected. But anyhow, the first pin is the programming voltage pin. And what the PIC 2 or 3 does when it's putting the 18F4550 into programming mode is it turns this on at a substantially higher than 5 volts voltage to make the chip enter programming mode. Pin 2 and 3 are just regular old power and ground, and pin 4 and 5 are our programming data and our programming clock. And of course you'll notice those match PGD and PGC on the chip. Now, one thing with these lines here is that when you're breadboarding or perfboarding your circuits, these are a sensitive digital signal. You want to keep these lines as short as possible, like half a foot or less. Really, the shorter the better. And pretty much all the circuit diagrams that I'll do with the 18F4550, I almost always put the programming header right here to keep these lines absolutely as short as possible. So now that we've considered our circuit diagram, we're ready to breadboard it. So now that we've considered our circuit diagram, we're almost ready to put our parts on our breadboard and test our circuit. But before we do that, let's take a look at these programming connectors, which are ideal for programming the 18F4550 when it's inserted into a breadboard. What we have here is a 6-pin header on one side and a 6-pin header on the other side, and then stranded wire connecting the 2 headers. Of course, we want to use stranded wire so that we can bend them a little bit. And you'll notice the colors that we're using here are white, red, black, green, and yellow, which of course matches the white, red, black, green, and yellow on our diagram here. There are other alternatives to programming the 18F4550 when it's inserted into a breadboard. For example, you could hold either the PIC18F or 3 into one end of a header or a bent header, and then you would still sort of have to hold the header into the breadboard, but it gets a little awkward. They always want to fall out if you use these. It's really worth your time to solder up some nice breadboard programming connectors such as these. When I'm done with my 3-part video series on demo boards for the 18F4550, I'm going to make a separate video on how to solder these connectors up. Please keep an eye out on my YouTube channel for that. Okay, so one final aside before we get to our actual breadboarded circuit. For anybody out there who's not familiar with the breadboarding process, there are lots of great resources out there to learn about that. I'd rather not get into breadboarding, generally speaking, in too much detail because I'm trying to keep this video down to a reasonable length of time and keep the focus on working with the 18F4550 rather than breadboarding circuits in general. But there's plenty of other great resources out there if you'd like to learn about breadboarding. For example, if you go to Amazon.com and you type in robot building for beginners, probably the first search result you'll get will be this Robot Building for Beginners. This is the first edition, 2002, second edition, published in 2009 by David Cook. This book is excellent. This book starts out assuming no prior knowledge of electronics, so if you've never even held a multimeter in your hand before, you've never seen a breadboard before, this book will start you from square one and takes you through the process of designing a circuit, getting the parts for it, breadboarding it, perfboarding it, and then finally constructing this robot which follows the line. Definitely great instruction in this book, highly recommended. If you'd prefer not to go with the book, if you prefer to go with a YouTube video, there are some very good alternatives there also. If you type in breadboard, one of the first results that come up, in this case the first result, is this video here, 2-part series by Electronics Instructor, Introduction to Breadboard. I watched these videos through just the other day. They're pretty good videos. There's also quite a few other videos on YouTube that you'll be able to find that will help you out quite a bit. But honestly, I really would suggest, if you've never breadboarded a circuit before, purchase this book and go through building the robot. The information you get from this book will be invaluable, more than worth the 1870. Highly recommended. And here we have our completed breadboarded circuit. This is about the simplest breadboarded circuit you could possibly have. All we really have on it is the 18F4550 at the center with a stabling cap next to it, and powers and grounds, of course, and then 4 LEDs and 4 resistors and our programming connector. Your circuit might look slightly different based on if you have a different breadboard or if you choose to arrange your parts differently. But in any case, if anything here looks truly foreign to you or not familiar at all, I definitely recommend checking out those sources I mentioned just a moment ago. Those will help you get started with breadboarding if you're new to it. Something else to keep in mind is that the 18F4550 is an ESD, that's electrostatic discharge sensitive chip. You definitely don't want to handle the 18F4550 unless you're properly grounded. If you're not familiar with taking ESD precautions, once I'm done with my 3-part series on 18F4550 demo boards, I'm going to make a separate video on observing ESD precautions. Definitely you'll want to keep an eye out on my YouTube channel for that. And so now that we're done with our breadboarding process, the next step is to write the software that we're going to load into the 18F4550. Okay, so now that we have our completed breadboarded circuit, we're going to next write software that we're going to load into the 18F4550. And to do that, we're going to need 3 pieces of software to write the software that we're going to load into the 18F4550. And those 3 things are MPLAB, MPLAB C18, and the PIC18F or 3 standalone programming software. Now the good news on all 3 of these is that they're all free downloads directly from microchip.com. So let's take a look at those. The MPLAB, that'll be our integrated development environment. And MPLAB C18, that's the C compiler for MPLAB. And then PIC18F or PIC18F3 standalone programming software works with either the PIC18F or the PIC18F3 to actually physically load the program that we write into our 18F4550. So if we go to Google and we type in MPLAB, that'll take us right there, MPLAB Integrated Development Environment. and it brings up this page. Now this is the new offering that Microchip is developing now, MPLab X. This is a cross-platform and open source tool. It's written in Java, so it runs on both Windows, Macintosh, and Linux. But unfortunately it's still in beta at the moment. I'll probably do a future video on this on my YouTube channel, but for the moment let's stick with the tried and true MPLab, which is up to version 8. And so it says, you see it says here, go to the bottom of the page for free MPLab IDE downloads. It mentions some features, some nice screenshots and stuff. Eventually we'll get down to the bottom here, MPLab IDE version 8.76. And then we're going to choose Save As and save it to whichever directory you prefer to download into. I'll choose Demo Video Downloads. And to save time during the video, you can see I cheated here and downloaded it ahead of time. So once we have MPLab IDE, and then we're going to want to download the C compiler for MPLab. So if we type MPLab C18, and there we go, first search result, MPLab C18 C compiler. Now you'll notice at the top here it says buy it now. Don't let that phase you. The buy it now part is referring to the optimized version, which you would have to pay for. The non-optimized version is free. So you'll see at the bottom, special free instructions for academic light use available here. So the non-optimized version is called the light mode version. So that's what we want to get, MPLab C for PIC18 version 3.4 in light mode. Click on that. Now it'll ask you to create an account. Go ahead and create an account. Again, there's no charge for the light version. The only thing is they might send you some emails trying to get you to buy the pay version, but that's okay. It's not going to hurt you at all. You definitely want to go ahead and create that account, and then that'll take you back to this screen here, and then when you click on MPLab C18 3.4 Lite, it will let you download it. So once you've got that, now we need to download the standalone programmers for either the PIC18 or PIC18, whichever one you have. So PIC18, and there we go, first result, PIC18 development debugger. And here's the PIC18 page. Of course, Microchip's trying to move everybody over to the PIC18. That's their new introduction in terms of standalone programmers. But if you have the PIC18, this is the software that you want to get. PIC18 version 2.61. Now this is not, of course, the physical PIC18 that arrives in the mail. This is the software that works with the PIC18 to download the program that you're writing into the 18F4550. So you're going to want to download that, choose Save As, again save it to your usual download location, and now if you have the PIC18, you do an internet search on PIC18, you'll find this page pretty quickly. Now the PIC18, when it first came out, Microchip was trying to get everybody to use it only from within MPLab to load software into chips, but the standalone programming application for the PIC18 was so popular that due to demand, Microchip came out with a separate standalone programming application for the PIC18 also. But since it was an add-on later, you'll notice it's not featured quite as prominently at the top of the page. You'll have to scroll down a little bit, but eventually you'll find it. Here it is, PIC18 standalone programmer app version 1.0 for Windows. That's what you want to download, and choose Save As, save it to the usual location. So once you're done with those either 3 downloads or 4, depending on if you have the PIC18 or 3, you'll have these 4 files in the directory you downloaded them to. Go ahead and extract, preferably to the same directory, the MPLab IDE and the PIC18 or 3 or both. And the MPLab C18 compiler comes in its own executable. It's not in a zip file. So once you've unzipped everything, you'll want to install MPLab IDE. They're currently up to version 8.76, and double-click Setup EXE. I won't do that on this computer because it's already installed, and it might confuse it. But anyhow, the installer for MPLab is very good. I've never had any problems installing anything I've downloaded from microchipdirect.com. Basically, if you just choose all the defaults and let the installer do what it thinks best, it's almost for certain going to work out well for you. Once you've installed MPLab, then you're going to want to install MPLab C18, the C compiler for MPLab. So again, double-click on this. I'm not going to do it because it's already installed. The installer's good. It's pretty straightforward. You shouldn't have a problem there. Then the last step you're going to want to do is install the standalone programming software for either the PIC18 or the PIC18, whichever one you have, or both. Again, there's a setup executable file in those downloads. It's pretty straightforward. So once you've done all that, either on your start menu or on your desktop or both, you should have some shortcuts here. One will be to MPLab, and then another one will be to either the PIC18F or the PIC18F or both. So at this point, we're ready to dive into MPLab and start writing the software that we're going to load into the 18F4550. So now that we've completed downloading and installing the MPLab integrated development environment and also the MPLab C18 compiler, we're ready to start writing software to load into our 18F4550. So we'll begin MPLab, and here's what the opening screen looks like. So if we go to Project and Project Wizard, and then next on the first screen, device. We definitely want to choose a device. You can see all the different devices here that you can possibly write software in MPLab to program all the various PICs, DS PICs, etc. We want to make sure to choose the 18F4550. PIC18F4550. If you ever start a project and by accident you don't choose the correct device to begin with, under Configure and Select Device, there is an option here to do that. Unfortunately, I found that if you choose the wrong device by accident to begin with, write a program, compile it, work with it a little bit, then you notice that, then you change the device later, ideally that should work perfectly, but in reality you can get into some problems with that. So when you're starting your project to begin with, you definitely want to kind of double check yourself here and make sure that you choose PIC18F4550. Then we'll choose next. Now this next screen, we can choose basically which compiler we'd like. So this drop down here gives you the choice of various installed compilers. What we want to do is we want to choose the Microchip C18 tool suite. So that'll be the Microchip C compiler. And you'll notice here it lists some of the various locations of the files, or some of the various files involved, and then here it lists the location of them. Version 3.40, that's that C compiler we downloaded earlier. So then we want to choose next. And now under New Project File, we want to choose Open. And now we want to create probably a folder for our project, and then also the project itself. So just to have this easy to find, I'll create it on the desktop for this example. So first let's create a new folder. And we're going to call this 18F4550. Blank internal clock. The reasons for calling it internal clock specifically is that later on in the third demo board that I'm going to show you, the USB demo board where we use the external clock, for testing purposes we're going to make a Blink program that uses an external clock to test to make sure the clock is working right before we do the rest of our circuit. So you always want to have a Blink program with an internal clock and an external clock on your computer. That allows you to, during the debugging process, you can just get a LED blinking, and that's kind of like taking the heartbeat of the chip to make sure you have everything wired up. So you'll want to keep this program as well as that one on hand for future reference, and then also that's why we're using this separate name, internal clock. And then I'm going to do a Control-C to copy that name. That's going to make it easier in the next steps. So now if we navigate into that directory on our desktop, 18F4550 Blink internal clock, and then under file name, I'm going to paste what I copied a moment ago, 18F4550, make sure my spelling's right and everything, Blink internal clock. Okay, that looks good. And then we're going to choose save. So now here it states where we just chose to save it to. So there's the folder and there's the project name. Then we're going to choose next. And the next step is add existing files to your project if you needed to. In this case, we're just going to make one C file for it when we start the project, so we're going to leave this blank here and choose next. And then there's our summary and finish. So the next thing I'm going to do is I'm going to open a Windows Explorer and navigate to the directory we just created so we can see the files that the IDE creates for us as we go. So let's see, where would that be? Blink internal clock. There we go. So once we created the original project, there's three files. There's blinkinternalclock.mcp and mcw. These are the two project files. If you ever want to open the project again later on, you can double click either of these rather than going to MPLab first and going to File Open or Project Open. So here we are in our project. So in other words, for example, if we close, it'll ask, do you wish to save the workspace before closing? Yes, we do. So for example, let's see, we came to our desktop like this someday. Here's our folder. Then we could just double click on either of these and it would take us right back into our project. So here's our project. It doesn't have any source files, header files, object files, anything like that yet. So what we're going to do is we're going to go to File, New. And we have to, before we can save it, we have to type something, so I'll just type a comment. Now if we go to Save, now note, unfortunately, MPLab in this case, we were just working in this directory, but it doesn't always take you to the directory you just created or saved something in. So make sure that you navigate to the correct directory that you're trying to save something to. In this case, it did take us to that same directory, but it doesn't always. And then we're going to add the file name here. So 18F4550 blink internal clock.c, and double check that we're saving it in the correct directory, 18F4550 blink internal clock. Another thing that's a little bit of an oddity of MPLab is once you're in a project and you create a new file, you might think it would automatically add that file to the project. Unfortunately, it does not. You have to check this box here at the bottom, add file to project, and then click save. So double check we're in the correct directory. We have the correct file name with the .c after it, and add file to project. That looks good. So if we do save, we can now see the C file appears over here in our file browser. So let's resize it so we have the whole screen to work with. And this bottom window here, when we compile things or search for stuff in certain files and so on, this will be our output for that, but we'll get to that later. So we've resized our main window here. And I'm going to copy and paste the name again, 18F4550 blink internal clock.c. And now we're ready to start writing our code. So if we do a file save and then compile, well, it's going to fail to build because we don't have anything in it yet, but that's okay. And that's how we will do it once we have something to compile. There's the build all button. Okay, so the first thing that we have to do when working with the 18F4550, and if you're used to writing desktop software but you've never written embedded software before, this is going to be a little bit new. But we have to do our chip configuration options. And then put a comment line all the way across. Now this next step here, this chip configuration option list, this isn't going to be the most fun or exciting programming in the world, but it's absolutely essential you don't skip this step. Basically, the 18F4550 has a whole bunch of features that it can perform. It can check itself. You can set certain things by default, like the clock and memory area protection and so on. And the microcontroller will try to correct what's going on. But in most cases, you don't want it to do that. You just want it to kind of leave stuff alone and run your code. So to make sure it does that, what we need to do is we need to go to Help and then Topics. And then we'll find under Language Tools here, PIC18 config settings. And then we're going to navigate to the 18F4550. Oops, that's the 4450. And there's the 4550 down there. Okay, 18F4550. So here we'll find all the different chip configuration options. There's quite a few here as we go down our list. Definitely what you'll want to do is you're going to want to print this list out. And it prints out to 5-6 pages, roughly, depending on how you have your printer set up. But in any case, each setting here, they list what the setting is. So this is how you would set it in code, PLL_div, and then there's a quick description of it. Unfortunately, you'll notice in the description it does not list what the defaults are, which is another good reason not to leave these as the defaults. I can't emphasize that enough. What's going to happen if you leave these as the defaults, you do the tempting thing and skip this step, is at some point the microcontroller will start clearing itself automatically unbeknownst to you, or the watchdog timer will kick on, or memory protection for something you're trying to change will kick on. Some really weird behavior that you won't be able to figure out at first will happen because you didn't set the default options. So let's take the time to go through and set these now. Now the first 3 options, actually the first 4 options, are pertaining to the clock. PLL_div, that's phase lock loop prescaler selection bits, system clock post-scaler selection bits, and then USB clock section bit. So if you refer to the 18F4550 datasheet, one of the first sections in the 18F4550 datasheet is the section on the clock, or the oscillator as it's listed. And it's a big data sheet, so it might take a moment to come up. There we go. But if we go to section 2 here, oscillator configurations. Once you get into using the external clock, you're definitely going to want to read this section, and especially you're going to want to take a look at this diagram here. It explains the clock options extremely well. But for now, for this demo board, what we're going to want to do is we're basically going to want to use the internal clock, and that will involve setting this fourth option here. And then the previous three options, essentially it doesn't really matter what we have them set to since we're going to be using the internal clock. So let's go ahead and do that. So we're going to type pragma config. That's the statement that we're going to start with when we're setting all these options here. So we're going to type pragma config pll div is assigned 5. So this does not matter since we are using the internal clock. For now, of course it will matter later when we're using the external clock. And then we'll do pound pragma config. Probably a good idea to copy and paste pragma config with the space after it. That way you won't have to keep typing it. So now referring to our compiler options list here, the next option is CPU div. So we're going to type CPU div is assigned OSC1 underscore PLL2. So again, where you get what you could potentially assign CPU div to is from this list here. Here's your choices: OSC1 PLL2, OSC2 PLL3, OSC3, and so on. Okay, I need up my spacing here, and since I'm going to say the same thing, I'll just copy and paste it. And the third clock option that for the moment does not matter, pragma config USB div is assigned 2. And again, this doesn't matter since we're using the internal clock. Now, I happen to choose values for these that are going to be similar or exactly the same as the values that we're going to use later on when we are using the external clock, so we won't have to change much when we get to that. But for the moment, we'll leave them as that. So now the next setting, FOSC, gives us quite a few choices here, as we can see, depending on whether you're using an internal clock or an external clock and which pins you'd like to be able to use with that. So what we're going to do is we're going to do pragma config FOSC is assigned INT-O SCIO EC. And that's short for internal oscillator, input output, and the EC oscillator. So let's comment that. So I'm going to make this a 2-line comment. So in other words, we're going to use the internal clock, pin number 14, there we go, which is also RA6. If we refer to our circuit diagram, you can see that OSC1 and 2, these are the two pins that you would connect an external clock to if you were using an external clock, which we're not. So pin 14, RA6, with the setting we're choosing, we could use as an input-output pin. So pin number 14, which is also RA6, as an I/O pin. And pin number 13 is unused. And we also, here we want to note that if the OSCON register, and I'm going to get into registers in more detail in the second video with the I/O demo board, but for now all we really need to know is that if the OSCON register is left as the default, the clock speed will be 1 megahertz, which is more than fast enough for the LED blinking application we're going to do today. Now, for the remaining options, which are substantially less confusing than the clock options, I'm going to fast forward the video at this point because there's so many to type in. But to make a long story short, if anything is unclear, see my comments. If that doesn't make it clear, see either the datasheet, 18F4550 datasheet, or this list here, and hopefully it'll make it more or less clear, or at least clear enough. But basically the idea is this. For all these things, code protection, write protection, if you're not sure what it is, you probably want to turn it off. That's really your safest bet. So let's enter all those options now. Okay, so that completes our chip config settings. Now we can get on to something that'll look more like you would think a typical C program would look that you might be used to. So we're going to start with #include, and the file we're going to include is lowercase p 18 lowercase f 4550.h. That will tell the C18 compiler what options to use throughout the rest of the program. Next, we're going to have one function in this program. It's going to be called delay. So just like any other C program, we need function prototypes. And we're going to comment line over for readability and void delay. Let's just call it delay. Now, one thing I will say about the C18 compiler is a lot of compilers, like the Microsoft Visual C++ compiler, for example, you could not include that void there and it would make no difference. This compiler is substantially more sensitive to that. You always want to include the void in the brace there. Otherwise, it'll start giving you errors about no function prototype and so on. So now we're ready to write function main. So basically, we're going to have to set up our tri-state register for port B, and that'll be 4 statements, and then we're going to have an infinite loop that essentially turns the LED on and off and then delays long enough for us to see it. So here's how we're going to do that. First we'll have a comment line, then regular old void main void, now for the different registers in the chip, we can refer to those with names in our code here. And how you would know which registers to refer to by name is there's 2 ways. One is the datasheet. So let's take a look at that. And the register we're going to start with is the TRIS register. That's tri-state register, which determines whether certain pins on certain ports are input or output. And we're specifically interested in the TRIS-B register. So for example, if we type TRIS-B in the datasheet, and let's go down one more. Here's the special function registers map. So there's a register at this location within the microcontroller that the internal circuitry will check. And then depending on the state of that, the microcontroller will either make the corresponding pins of port B input or output. And if we continue on in the datasheet, in this section here, I/O ports, it gets into port A, port B, and so on. You can see these sections of the datasheet for more detail. Another option is if we go to where the C18 compiler was installed, which on my particular computer is going to be program files. You'll have to check your install location, might be a little bit different, but it'll probably be something at least similar to program files microchip MPLAB C18 version 3.4 and then .h. So what you're going to want to do is now you're going to want to navigate to the P18F4550.h file. And there we go, P18F4550.h. And you're going to want to copy this file, right click and drag and copy it. Make sure you don't move it out to your desktop because then it won't be there for the compiler to use anymore. Then you'll copy this file on your desktop to refer to. Now that's going to be invaluable to you because if you open that with something like Notepad, WordPad, whatever you prefer. Whoops, didn't mean to do that. This is the .h file that the MPLAB C18 compiler actually uses to go through your code and check on what you've written and how it corresponds to the different registers. So here we see all the different registers that there are. So the UIR register we'd refer to as UIR bits, or we could refer to it as UIR if we wanted to do the entire register, and so on for all these different registers. So for example, I'll press Control F here to do a search. We're looking for the tris-B register. So if we type in tris-B to me there. So here we are, tris-B. So we could refer to the entire register as tris-B or to the individual bits of it as tris-B bits dot, and then either tris-B0, tris-B1, tris-B2, or RB0, 1, 2, etc. So here's what we're going to do in code to set the port pins RB. Remember what we're trying to do, going back to our diagram, is we're trying to set these pins here, RB0, 1, 2, and 3, to output so that we can blink these LEDs. So here's how we're going to do that. We're going to type tris-B bits dot tris-B0 is assigned. Now a 0 will set that pin, the RB0 pin, in this case of our particular chip here, that's pin 33. A 0 will set that to output, whereas a 1 will set it to input. So let's comment that. So set RB0 to output. And then to make life easy on ourselves, we'll copy that same statement. And then we'll also do the same thing for the other 3 LEDs. So tris-B bits dot tris-B1, tris-B2, and tris-B3. We're going to set all those to 0. So that's going to set RB0, 1, 2, and 3 all to output. So at this point, we've set these 3 pins here, pins 33, 34, 35, and 36 to output so we can blink our LEDs. Now the next thing that we're going to do, that's it for the configuration really, so now we're ready for the actual while loop that infinitely blinks the LEDs. So since we want to loop forever, we're going to type while 1, and then we're going to type port B bits. So for example, you could refer to the register that actually commands a microcontroller to set the output state of these pins with the command port B. So we're going to type port B bits dot RB0, and that's going to set, it is assigned to 1. So that's going to apply 5 volts, if we go back to our diagram, to pin 33, which is RB0, which will be sufficient to turn on LED 0. So let's comment that, turn on LED 0. Okay, then we're basically going to do the same thing 3 more times here, so to make life easy on ourselves, let's copy and paste it. So we're going to turn on LED 1, 2, and 3. And to do that, we're going to set port B bits dot RB0, 1, 2, and 3 all to 1. So now the LEDs will be on. So the next thing we need to do is we need to call our delay function to pause with the LEDs on for just a moment so that our eyes can see the LED turning on and off. Then what we're going to do is we're going to turn the LEDs off and pause for just a moment. So again, to make life easy on ourselves, we'll copy and paste. So we're going to have port B bits.rb0, but now we want to turn it off. So we'll make that a 0, and the other three the same. And so that's going to be turn off LEDs 0, 1, 2, and 3. And then of course we call our delay function again to pause for just a moment while the LED's off. And that's going to end our while loop, and that will end function main. Now all that's left is to write our delay function. So I'll add a comment line to make the readability a little better. And we're going to do void delay void. Again, don't forget the second void. And we'll have two variables, and I and j. And we're going to do for I is assigned 0, while I is less than 1,000, I plus plus. And that'll be our outer loop. Then for our inner loop, we're going to type for j is assigned 0, while j is less than 2, j plus plus. Now let's put a comment in here, delay. And then we're going to end the inner for, and end the outer for, and end the function. And then save and compile, and see if we made any typos or not. I must have made a typo somewhere. Let's see. Pragma config. Oh, I accidentally typed config twice here. And so if we do a compile again, did I make any more typos? No, I didn't. Build succeeded. So let's go back to the folder where we created all the project files in before. So let's just go back to the desktop, double click the folder, there we go. So you recall before there were the two project files and then one other. Now there's more here. So the development environment internally uses these COF files and the O file for the managing the environment and the compilation process and all that. We don't need to worry about that. The two other files that weren't here before that we do need to keep an eye out on that we should take a look at are this C file here. Of course, we created that. You'll probably remember that when we first created the project, the next thing we did was we created the C file and then typed in our code. And the last file that's especially important to us is this hex file. This is the file that's the actual machine code that we're going to, using either the PIC18F or the PIC18F3, that we're going to load into the 18F4550. So once this file is created, we're now ready to do that, and that's our next step. Okay, so we've designed our circuit, and we've breadboarded our circuit, and we've written software to load into the 18F4550. So now we're ready to go ahead and actually load the software into the 18F4550. So to do that, we're going to use either the PIC18F or the PIC18F3. I'll demonstrate both. When you get either of the PIC18F or the PIC18F3, they'll come with their own USB cable. Here's the one for the PIC18F, it's black. And here's the one for the PIC18F3, it's this nice red color. It really doesn't matter though, it's physically the same cable in either case. So what we're going to do is we're going to plug the USB A end of the cable into our computer. And then we're going to plug the USB B end into the top of the PIC18F. Now of course the PIC18F is a USB device, so when we plug our USB cable that goes from the computer into the PIC18F, we should get the doink, indicating that the operating system has found the PIC18F. Also another thing to notice with the PIC18F is we've got three LEDs here, power, target, and busy. Power is on when the computer is powering the PIC18F. That doesn't mean that the power LED that is does not mean that the PIC18F is actually connected to the chip yet. And the busy LED is the other one you'll want to keep an eye out on. The busy LED will flash when the PIC18F is doing something such as programming. So let's plug it in. Here are the doink. There we go, the operating system found the PIC18F. And now we're going to connect the PIC18F to our breadboard. So here's our breadboarded circuit, same as in the picture shown earlier. Especially take note of this nice 6-pin connector, actually 5 because 1 pin isn't used, programming connector that will allow us with ease to connect the PIC18F to our breadboarded circuit. So now we'll go ahead and connect the PIC18F. And now we're ready to go into our PIC18F standalone programming software. is on our desktop. And there we are. I'll zoom in just a tad more. And out just a bit. There we go. That should be good. So, if we double click PIC18F4550, here's the window that comes up. So you'll notice a few things already have been done for us. This device here, PIC18F4550, that wasn't pre-entered. That's the PIC18F realizing that it's connected to the 18F4550 already. That's part of the auto detection user-friendly process of the PIC18F. Also, we get this nice message here, PIC18F found and connected, PIC device found. So it found the chip, everything's working great so far. So now let's go to File, Import Hex, and we're going to navigate to the hex file that resulted from our compilation process earlier. So here we are, 18F4550 blink internal clock.hex. Double click that, and we should get this friendly message here, hex file successfully imported. Now we're ready to write. Now there's some other features in the software, read, verify, erase. You can look at program and data memory, but for now let's not worry about that. Let's just get to writing the program into the chip. So when we choose write, you'll notice if you have LEDs connected to the chip, you might get them blinking. In this case, they will blink because of the pins they're connected to. And there's the blinking, and there's the programming process done. So now we have the nice user-friendly message here, programming successful, the bar is all green, the progress bar is full, so we know the programming process was successful. If it's not, the PIC18F is very good about giving us errors that will help us diagnose what's wrong with the programming process if something goes wrong. Usually if something goes wrong with the programming process, just as a general troubleshooting tip, it probably means that you made the programming data or clock lines too long, or that there's some kind of noise on them. That's usually what it comes down to. But in any case, the programming process went great for us here. So now on the right side of this software here, we have VDD PIC18F. So once we check this box, the PIC18F through its power and ground pins, pin 2 and 3, will apply power and ground to our board. And it's going to apply however much voltage we choose here, so in this case 5 volts. So now let's zoom out just a tad, and now I'll check the box and the LED should blink. And there we have it. So we've successfully written our software and loaded it into the 18F4550 and tested it with the PIC18F. So now let's demonstrate the PIC18F3. Okay, so now we're ready to use the PIC18F3 to program our circuit. Here's our PIC18F3. You'll notice that Microchip changed the names of the LEDs to power, active, and status from the different names on the PIC18F. It doesn't really matter though, they essentially do the same things. We plug in the B end of the USB cable to the PIC18F3 just as we did with PIC18F. Just a little bit of a delay. And there it is, the operating system recognizing it. So now we're going to connect the PIC18F3 to our programming connector just as we did with the PIC18F. And we're ready to enter the PIC18F3 standalone programming software. Now before we do that, I should mention the PIC18F2 standalone programming software was around for a long time, and Microchip refined it and made it very user-friendly. The PIC18F3 standalone programming software is a relatively recent release. It's still in version 1.0, so it's not as user-friendly yet. Hopefully Microchip will continue to improve on that as time goes on. So we double-click on that, and that'll take a moment to come up. I'll zoom in during that time. And there we are. So the first major difference you're going to notice versus the PIC18F2 software is our chip was not, I'm going to zoom in adjustment there. There we go. Our chip was not auto-detected. Under device it says PIC10F200. Of course that's not what we have connected to our board at all. So we have to choose 18F4550 from our list here. 18F, where are you? PIC18F4550. There we go. Okay, now we're going to do the file and import hex process just the same as before. On desktop, 18F internal clock blank, internal clock.hex, and there we are, our hex file is imported. So now we're going to choose write, and I'll pan out so you can see the lights blinking again while we're writing. And you'll notice the status LED on the PIC18F3 blinks red while it's programming, and that'll be a solid green when it's done programming. And it's still going, and there we go. So you'll notice although the status light of the PIC18F is solid green, the PIC18F standalone programming software doesn't give us as friendly of a message indicating programming is complete as the PIC18F software did. But in any case, our programming is done, so we can go to this side on this area on the right here now. Once we check the on box again, 5 volts will be applied, so we'll pan out and then do that, and hopefully we'll get some blinking LEDs. And there we are, blinking LEDs. So we've successfully used the external programming software to program our chip with the PIC18F. Now the next thing we're going to take a look at is using MPLab to program the 18F4550 with the PIC18F. Okay, so as a final option, let's consider programming the 18F4550 with the PIC18F through MPLab. Now when Microchip first developed the PIC18F, they really did it with the intention of all the programming being done through MPLab, and then this standalone software here, PIC18F, was added later on as an option. So let's take a look at how Microchip really intended for us to do it. If we go to our project, click either project file, that'll open MPLab for us. And let's zoom in. So the first thing we're going to do is we're going to go to Programmer, select Programmer, and then PIC18F. And we'll get some messages on the output window here, as well as this voltage caution message. So what this message here is telling us is that if we had selected a chip from within MPLab that was a 5 volt chip, but we connected the PIC18F to a board with a 3.3 volt chip on it, that we could harm the chip. But that's okay. We know we're connecting to a 5 volt chip, so we're not going to hurt anything. So we can choose OK. And now some more processing is going on, and in a moment here the output window will come up with an error. So it says PIC18F connected, but then it says this error here. And the reason for this error is that there's no power on yet. Now if we look at these buttons at the top here, there's a power button and a programming button, but they're both grayed out. So what we have to do is go to Programmer, Settings, and then Power, and we're going to check this box, Power Target Circuit from PIC18F, and when we do that, 5 volts will be applied to the chip. Now I'm going to pan out when we do that. Since we just programmed our chip a moment ago with the external software, there's already the program loaded into it. So as soon as we apply our power, it's going to give us that warning message again. Just choose OK. And the power is now on, so our LEDs are now blinking. But we haven't programmed it. We sort of cheated effectively because the program was already in there from earlier. So let's illustrate how we would program it if it wasn't already programmed. So if we choose OK, again, it keeps giving us that warning message over and over. It's really trying to protect us from harming the chip. So now if we were to go up here, final adjustment here, and this button here will turn the power off. The power's off, can't see it on camera, but the LEDs are now not blinking. The power on and off button is not grayed out, but these other buttons are grayed out. So if we turn the power on, of course it gives us a warning message again. And now that the power's on, the LEDs are blinking, and these other buttons here for the programming features are enabled. So if we choose Program, we finally get a message that says Programming, Verifying Programming Complete. So that's how you program the 18F4550 with the PIC18F via MPLab. So at this point, the one remaining thing we have to do in our project is to make a perf-boarded version of our circuit so it's more permanent. We have something soldered up rather than only a temporary breadboard version. Okay, so we've breadboarded our circuit and we got it working. So our final step is we're going to solder up a perf-boarded version of our circuit so that we have something more permanent. Now if you're new to soldering or perf-boarding, there's some real good resources on YouTube for instruction in those areas. If we do a YouTube search on EEV blog soldering, among the first results that pop up will be EEV blog episodes number 180, Soldering Part 1 Tools, number 183, Soldering Tutorial Part 2, which covers through-hole soldering, and then number 186, which covers surface mount soldering. If you've never soldered before, definitely check these 3 videos out. Excellent instruction. If you've soldered before but you're new to perf boarding, if we type perf board, one of the first results that comes up is this video here, Circuit Skills Perf Board Prototyping. Now I cheated and downloaded that video ahead of time in a separate window. So this video is by this person, Colin Cunningham, and in this video he shows how to make this pulse width modulation guitar effect circuit on a perf board. So first, the author Colin Cunningham goes into some kind of background about what perf boarding is and some of the different options there are in terms of the perf boards you can get. And then he shows some examples that he's done. And then starting with this pulse width modulation guitar effect circuit diagram, then he shows the steps of putting the parts on the board and soldering them and so on, going through a completed working perf boarded circuit. Excellent instruction. Definitely, if you've never perf boarded a circuit before, check this video out. It'll give you a great idea of how to go about it. Great footage. Highly recommended. And here we have some still images of our final perf boarded circuit. If you're new to soldering and perf boarding, perhaps you're watching this video with a software background and you're looking into getting into soldering and circuits, this would be a great first perf boarded circuit to solder up because it's very forgiving. There's very few parts, very few solders, very few connections. Great place to start. Also bear in mind as you're looking at these images that perf boarding is a matter of preference to some degree, a matter of style to some degree. You could run traces along the bottom, you could run wires along the bottom, you could run wires along the top, you could arrange the parts differently on the board, you could use different size boards since there's so much extra room here. There's different ways you could go about it. There's really no right and wrong. It's really whatever you find would work best for you. And here's some final footage of the perf boarded version of our demo board being powered by the PIC18F4550. Congratulations! You now know how to make your own demo board and program the PIC18F4550. So, what's next? In our next demo board video, we'll add both digital and analog input, and in our third video, we'll demonstrate USB communication. Stay tuned. Please see my website on the internet, www.18f4550.com, and my YouTube channel, 18f4550 videos. Happy programming and soldering!